Friends, welcome to my YouTube channel. Tanish here. In this video, I am going to discuss about quantum tunneling. It's an interesting concept. To illustrate quantum tunneling, consider a ball rolling along the surface with a kinetic energy of 100 joule. Let's assume as the ball rolls, it encounters a hill. To get clarity, you can see this figure. See, as the ball moves, it encounters a hill. The energy needed for the ball to climb the hill is 1000 joule. The ball proceeds only part of the way up the hill, stops and returns in the direction it came based on the laws of classical physics. But you need to understand, we do not expect even after repeated attempts for the 100 joule ball to ever be found beyond the hill. Therefore, the probability that the ball passes over the hill is exactly 0, and probability it is turned back or reflected back by the hill is exactly 1. The ball never makes it over the hill. The existence of the ball beyond the hill is an impossibility or energetically forbidden. So now, what is this quantum tunneling? That's what I am going to discuss now. This is possible. See, we understood that in classical physics, it's not possible for the ball to climb the hill with 100 joules of energy. But this is possible in quantum level or atomic scale. Quantum tunneling is the quantum mechanical phenomenon where a wave function can propagate through a potential barrier. Quantum tunneling is a phenomenon in which particles penetrate a potential energy barrier with a height greater than the total energy of the particles. So you understood what? Quantum tunneling was first noticed in 1927 by Frederick Hunt, a German physicist. Max Born, who was instrumental in the development of quantum mechanics, recognized the generality of tunneling. See, here I have shown the tunneling in diode. I will explain that. See, Max Born realized that it was not restricted to nuclear physics, but was a general result of quantum mechanics that applies to many different systems. The study of semiconductors and the development of transistors and diodes led to the acceptance of electron tunneling in solids by 1957. It's shown in the figure. This is electron tunneling in diodes. In 2016, quantum tunneling of water was discovered. In the year 2016, water molecules breaks bonds through quantum tunneling. Now we are going to discuss about the interpretation why this quantum tunneling occurs. The reason for this difference between classical physics and quantum mechanics comes from the treatment of matter in quantum mechanics as having properties of waves and particles. One interpretation of this duality involves the Heisenberg's uncertainty principle, which defines a limit on how precisely the position and the momentum of a particle can be known at the same time. So you are familiar with this equation, delta x into delta p greater than or equal to s by 2, where h is the Planck's constant, is 6.632 into 10 raised to minus 34 joule seconds. Delta x is the uncertainty in position and delta p is the uncertainty in momentum. See, this implies that the uncertainty principle implies that there are no solutions with a probability of exactly 0 or 1. Though a solution may approach infinity if, for example, the calculation for its position was taken as a probability of 1, the other, that is the speed or momentum, would have to be infinity. Hence, the probability of a given particle's existence on the opposite side of an intervening barrier is non-zero, and such particles will appear on the other side with a relative frequency proportional to its probability. That's what Heisenberg's uncertainty principle says. Now we will get into the applications of this quantum tunneling, the practical applications, and even some phenomenon in this universe. See, you need to understand tunneling occurs with the barriers of thickness around 1 to 3 nanometer. Nano means 10 raised to minus 9, right? See, 1 to 3 nanometer and smaller. But is the cause of some important this is the cause of some important macroscopic physical phenomenon. For example, I can tell you one important aspect is the nuclear fusion in stars. The nuclear fusion in stars, you can understand. You may be familiar with the fission and fusion reactions. Quantum tunneling is essential for nuclear fusion in stars. The temperature in stars' cores, the central part, is generally insufficient to allow atomic nuclei to overcome the Coulomb barrier. Coulomb barrier means Coulomb's force of attraction or repulsion, and to achieve thermonuclear fusion. So quantum tunneling increases the probability of penetrating this barrier. That's what quantum tunneling does. That's what it's shown in the figure. You know, the hydrogen nucleus and helium nuclei formed from hydrogen nucleus. They combine to form helium, then beryllium. You know the process. So though this probability is still low, see, you know, the quantum tunneling, the probability of this quantum tunneling is still low. The extremely large number of nuclei in the core of a star is sufficient to sustain a steady fusion reaction for millions or billions or trillions of years. A precondition for the evolution of life in isolation in the habitable zones. Our sun can be treated as a good example for this kind of tunneling effect. This is one application. We can see it in the nature itself, application of quantum tunneling. Next one I am going to discuss is radioactive decay. So what is radioactive decay? You are familiar. Radioactive decay is the process of emission of particles and energy from the unstable nuclei of an atom to form a stable nuclei or a stable product. This is done via the tunneling, quantum tunneling of a particle out of the nucleus. Here we call it as the electron tunneling, or in radioactivity we call it as electron capture. This is the one important application of quantum tunneling. So now you understood that. Now I will tell you another important application of quantum tunneling. That's just 1 second. It is quantum biology. It's really interesting. See, many aspects in quantum biology. It's there. I can show you. See some of the aspects in the figure. It's shown. You can understand it. See, even the migration of birds is the application of quantum tunneling. So we will discuss in detail some of the applications. Quantum tunneling is among the central non-trivial quantum effects in quantum biology. Here it is important both as electron tunneling and proton tunneling. Electron tunneling is a key factor in many biochemical redox reactions like photosynthesis, cellular respiration. You may be familiar with aerobic and anaerobic respirations, as well as enzymatic catalysis. How enzymes are working in our human system or in any animal. It's due to quantum tunneling. Here we can understand it as proton tunneling is a key factor in DNA mutation. Proton tunneling is an important factor in DNA mutation. That is the application of quantum tunneling in quantum biology. Now some other applications we will see. Applications of tunnel field effect transistors. It's another practical application. See, a European research project has demonstrated field effect transistors in which the gate we call it as channel, right, is controlled by a quantum tunneling rather than by thermal injection, reducing gate voltage from 1 volt to 0.2 volts and reducing the power consumption by 100 times. If these transistors can be scaled up into VLSI chips, they will significantly improve the performance of the integrated circuits. That's another application. Next is scanning tunneling microscope. That is another application you can see. The another important practical application in our, even it can come to our day-to-day life. The scanning tunneling microscope, we call it as STM, invented by Gerd Beining and Heinrich Rohrer, may allow imaging of individual atoms on the surface of a material. It operates by taking advantage of the relationship between quantum tunneling with a distance. That's another application. Now, this is the final point I want to discuss. That is quantum tunneling faster than light? See, when we discussed about this one, what was that phenomenon? Quantum entanglement. We understood this entanglement is, faster than light. In the same way, there is research is going on. Is quantum tunneling is faster than light? See, some physicists have claimed that it is possible for spin zero particles. Spin is an important quantity which represents the momentum of an atomic particle. So spin is really important in quantum mechanics. So for spin zero particles to travel faster than speed of light when tunneling, this apparently violates the principles of causality, since there will be a frame of reference in which it arrives before it has left. So that's what it's a question whether it's possible or not. Is quantum tunneling faster than light or not? Other physicists, some physicists such as Herbert Winful, have disputed these claims. Winful argues that the wave packet of a tunneling particle propagates locally. So a particle can't tunnel through the barrier non-locally. Winful also argues that the experiments that are conducted to show non-local propagation have been misinterpreted. So that's about whether quantum tunneling is faster than light or not. That's all about quantum tunneling. Thanks for watching. Please like, share and subscribe. Thanks a lot.